In the last class, we had introduced diffraction. Interference refers to a situation where we have the superposition of two waves or a few waves, and we use the term diffraction in a situation where we have the superposition of many waves. So, in today's class, let me first recapitulate what we had been discussing in the last class, and I shall continue from there. So, diffraction occurs, one of the situations where diffraction occurs is when I have a wave incident on an aperture like the one shown over here. So, in this situation we have a plane wave. The plane wave is incident on an opaque screen. In that opaque screen we have an aperture. So, the wave can pass through the opaque screen only through the aperture, and we are interested in the intensity pattern that this aperture would produce on a screen, on another screen which is placed far away from the aperture. So, the question is, how do we handle such problems? And in the last class I had told you that we can apply the Huygen-Fresnel principle to handle such problems. So, what is the Huygen-Fresnel principle? Let me just first recapitulate this. Huygen had introduced a principle to follow the evolution of waves in arbitrary media. So, Huygen's principle can be applied to follow the propagation of light, for example, in an arbitrary medium. So, this is the wave front at a time t equal to 0, and we would like to determine where is the wave front at a time, where is the same wave front at a time t equal to capital T. And Huygen's principle tells us that each point on this wave front at the time t equal to 0 acts like a source for a secondary wavelet. So, we should draw a secondary wavelet originating from sources, and each point on this wave front acts like a source. So, at a later time capital T, t equal to capital T, the secondary wavelet emitted from this particular source looks like this source looks like this, and we are supposed to do it for all the sources, every point on this wave front. And then to find the wave front at a later time, we should consider the envelope of all of these wavelets. So, a plane wave evolves into another plane wave which is shifted, a spherical wave evolves into another spherical wave of a larger radius, and the Huygens principle is not very useful if you are dealing with the propagation in vacuum, but if you wish to study the propagation of light in an anisotropic medium, for example, where the speed of light is dependent on the direction in which the light is going, the Huygens principle is very useful. Now, this does not tell us anything about diffraction. This was generalized by Fresnel. So, the Huygen-Fresnel principle is as follows: when we have a wave incident on this aperture, then every point on this aperture acts like a source for secondary wavelets. So, every point here acts like a source for secondary wavelets. It emits secondary wavelets which are spherical waves. So, if I wish to calculate the resultant, the wave, the intensity or the wave produced by this aperture at some point here on the screen, we have to superpose the secondary wavelets emitted by all of these sources. So, every point in this aperture acts like a source. To find the resultant wave at a point here, I have to superpose the contribution from all of these points. Here I have shown you the contribution from only 2 points. So, this point emits a secondary wavelet, and this secondary wavelet propagates to this point over here. So does this point. This also acts like a source. This emits a secondary wavelet which again propagates here, and every point on this aperture does exactly the same thing. So, to find the resultant wave over here, I have to add up the contributions from all the points on this aperture. This is the Huygen-Fresnel principle. And then we had considered a particular problem. The problem was to determine the diffraction pattern of a single slit, and the slit that we had considered was rectangular. So, we have a plane wave incident on a opaque screen in which there is a rectangular slit which has been cut out. The rectangular slit, one dimension of the rectangular slit is d and the other dimension is L, and we had assumed that d is much smaller than L, and we would like to calculate the intensity pattern produced by this slit on another screen located far away. Now, we had assumed that d is much smaller than L, and if you take the limit of L going to infinity, where this length is arbitrarily large, this dimension is arbitrarily large, this essentially reduces to a one dimensional problem. We have to be concerned with only the dimension over here. So, through a section like this. Another point which I should mention, that in this particular situation we have a plane wave which is incident on the slit. Now, every point on the slit acts like a secondary source, like a source for a secondary wavelet. So, these spherical waves come out. We are interested in the intensity on a screen which is sufficiently far away, so that the secondary wavelets that come out from the sources in this slit may be, to a good approximation, treated as plane waves by the time they reach the screen. So, we have a plane wave coming into the screen, into the slit, we have plane waves going out. This situation where you can deal with plane waves, so where you can, the whole diffraction problem can be thought of in terms of only plane waves, is referred to as Fraunhofer diffraction. And we shall be restricting our analysis to only this situation. So, let me just remind you once more what we mean by Fraunhofer diffraction. In this refers to a situation where the incident wave is a plane wave and the wave that goes out is a plane wave. This is a suitable description provided the source which illuminates the slit is sufficiently far away and the screen where we want to study the intensity pattern is also sufficiently far away from the slit. In case any of these assumptions are not valid, if the screen is located near or if the source is near, then you have to take into account the spherical nature of the wave, and that situation is referred to as Fresnel diffraction. We shall not be considering this in our lectures. It is a little more complicated and we shall not be dealing with this. So, if you have a situation where the spherical nature of the wave is important, that situation is referred to as Fresnel diffraction. We shall be considering only the Fraunhofer diffraction. And we have made the assumption here that in the rectangular slit, one of the dimensions d is much smaller than L. So, we will take the limit where L becomes infinitely large, and the whole problem reduces to a one dimensional problem where it is only this direction which is important, the one along the smaller dimension of the slit. So, the whole problem now reduces to a one dimensional problem which I have shown over here. So, this is the smaller dimension of the slit d. This is the plane wave that is incident on this slit. Each point on the slit, in the slit, acts like a secondary source. That is what the Huygen-Fresnel principle tells us. Now, the point to note here is that the wave which is incident on the slit is such that the wave fronts are parallel to the slit. As a consequence of this, all the sources for the secondary wavelet emit the secondary wavelets at exactly the same phase. You should note that this would not be true in a situation where the wave, the incident wave, was at an angle and the wave fronts were like this. In such a situation, the secondary sources in this slit would not be emitting the secondary wavelet, the sources on this slit would not be emitting secondary wavelets with exactly the same phase. There would be a phase difference, this would be ahead and this part would lag in case the wave fronts were at an angle. But we are considering a situation where the wave front is parallel to the slit. So, all of these points are oscillating with the same phase, the wave over here is oscillating with the same phase, and each of these points acts like a source which emits secondary wavelets at the same phase. Now, we have shown the screen over here. You could either place the screen very far away, or what you could do is you could put a lens in front of the screen, put the screen at a finite distance. What the lens does is that all the waves incident at an angle theta, the lens focuses, brings all of these waves to a single point. So, if I had, so for the angle theta, all the waves incident on this lens at an angle theta, they are brought to a same point P over here. All the waves emitted from the slit, let us say like this, these are all focused to a point over here, and all waves which are emitted like this from the slit would be focused to another point somewhere over here. So, what the lens does is it brings together all the waves incident on it that are at a particular angle theta, it brings them together to a point. And to find the resultant wave at this point, we have to add up the contributions from all the sources located at each point along the slit. So, we have to add up the contribution from all of these points acts like a source. So, let us first look at a point, a small line element dy located near the origin. So, we shall consider the contribution from a small element dy. So, this length line element we shall call dy, and it is located at the origin. So, we will use the y axis, we shall align the y axis along with the slit. So, the slit, so we have placed the y axis in the direction of the slit, and the origin of the y axis is located at the center of the slit. And let us ask the question, what is the what is the contribution to the wave over here from the sources within the small line element dy located at the center of the slit at the origin, and we will call this dE theta because we are only interested in the waves emitted at an angle theta, that is what the lens brings to this point. So, dE theta is proportional to this line element because the number of sources increases if I increase this, and there will be some overall amplitude A tilde. So, the contribution from this small line element dy to the waves reaching here is dE is equal to A tilde dy. Now, let us ask the same question for a line element for a line element dy which is displaced from the center by an amount y. So, how much is the contribution from a line element dy which is located at a distance y from the center, and what you will realize is that the contribution from this line element dy which is displaced from the center it leaves the source at exactly the same phase as the contribution from the line element dy at the origin, but by the time it reaches the point P, it picks up a phase difference, and there is a phase difference because of the path difference between the path from the center and the path from this point. You see there is a path difference between these two waves to this point, and the path difference is this much. So, this path difference will cause a phase difference. So, the contribution from the line element dy, a distance y displaced by a distance y, can be written as the same thing as the contribution from the origin, but with an extra phase difference, and the extra phase difference arises due to the path difference. So, the phase difference delta arises due to the path difference, and it is 2 pi by lambda into the path difference, which is y sin theta, where theta is the angle over here, and we will write this as k into y. So, the point to note over here is that each point on the slit acts like a secondary, as a source for a secondary wavelet. All of these secondary wavelets emitted at angle theta arrive at the point P, at the same point P, with different phases, and the phase difference depends on the displacement from the origin, from the center of the slit. So, to calculate the resultant, you have to add up the contribution from all of the sources. This is what we had done in the last class. We had added up the contribution. So, this superposition of the contributions from all of these sources located at different points. So, there are sources all along the slit, you have to add up these contributions, and this is an infinite number of sources because this is a continuous variable y, and this continuous sum is represented by an integral. So, you have to add up the contribution from all of the sources, and this integral can be written as a tilde e to the power I k y dy from the, and the integral limits are minus d by 2 to plus d by 2. We had done this integral in the last lecture, and it gave us a tilde into d into sine k d by 2 divided by k d by 2. So, we had calculated this. To get an idea of get a physical picture of what this is all about, we are essentially adding up the contributions, the waves emitted from sources located all the way from here to here, and they are all emitted with the same phase, but by the time they reach here they arrive with different phases. Let us ask the question, in which direction theta do we expect to have the maximum intensity without doing the mathematics? Now, notice that if we look at theta equal to 0, all the waves would arrive at exactly the same phase, there would be no phase difference. So, all the sources would contribute at exactly the same phase, and they would all add up, all the waves from all of these sources would add up constructively, and we expect to get the maximum intensity. Let us now ask the question, where do we expect to get the minimum intensity? The minimum intensity, you can see, will occur when the phase difference between the wave coming from the center and the wave coming from the tip is pi. The phase difference between the center and one tip is pi. So, the phase difference between the center and the other tip is also going to be pi. So, you run from the phase changes from minus pi to plus pi. So, each of these sources contribute the same amplitude, but with a different phase, and the phase runs from minus pi to plus pi. Now, we all know that if you integrate e to the power I delta with delta running from minus pi to plus pi, e to the power I delta is cos delta and sin delta with a factor of I in front of the sin, and if I integrate this from minus pi to plus pi, then we get 0. So, the intensity is going to be minimum when the phase difference between this tip and this tip is exactly 2 pi, or the phase difference between the center and one of the tips is pi. The contribution from all of the sources now cancel out, they cancel out at the point where this phase condition is satisfied. Let us now go back to the exercise that we were doing. So, we had calculated the mathematical expression for the superposition of the waves emitted from the different points on the source on the slit, and now we use this to calculate the intensity. The intensity is half E into E star, and we have I naught. We had done this calculation in the last class. The intensity is I naught some constant into sinc square beta, where the sinc function which we have encountered earlier is sin x by x, and beta is pi d sin theta by lambda. So, this gives us the intensity pattern on the screen. In the situation where theta is much smaller than 1, the intensity pattern is a little simplified. In the situation where theta, you should remember that theta is in radians. So, when theta is much smaller than 1, beta is approximately beta d theta by lambda, and the expression for the intensity is I naught sinc square beta d theta by lambda. Instead of sin theta, you can now write theta. So, this gives the intensity pattern on the screen in the situation where theta is small. We shall be considering this situation in the rest of this lecture. So, let me now plot the intensity pattern as a function of theta. Before that, let me remind you what we are doing. So, we have a plane wave incident on this slit, and each point here emits in different emits secondary wavelets. So, if I wish to calculate and emits secondary wavelets, and this is incident on a lens, what the lens does is all the waves emitted at a particular angle theta, it focuses to a single point. So, the intensity corresponding to a certain value of theta you will get at a particular point over here. Theta equal to 0 would correspond to the center. As you increase theta, the point would move up, and you would get that intensity pattern which I just worked out on the screen over there. So, the intensity pattern looks like this. So, before discussing this, let me show you what the intensity pattern actually looks like. So, this shows you the intensity pattern. The red dashed curve over here shows you the intensity of the light that you expect to receive on the screen. Theta equals to 0 corresponds to the center, and that is where you have the maximum of the sinc function. The intensity pattern is given by the sinc function over here. You have I naught sinc square pi d theta by lambda. So, as theta, when theta is equal to 0, the sinc function sin x by x has a value 1. So, the intensity is I naught. So, this constant I naught is the value of the intensity at the center. As you move away from the center, the sinc function falls, it oscillates and falls. So, as you move away from the center, the intensity falls, and then the intensity goes to 0, and it rises again, and then again it goes to 0, and you have these oscillations. So, what you will see on the screen is you will see a bright spot at the center, then beyond this bright spot it will be dark, and then there will be another bright spot at some larger value of theta or a larger distance from the center, and then you will have another bright spot somewhere over here. In between it will be dark. So, you have these bright spots separated by dark regions on the screen over here, as you can see. So, this line, the height of this curve shows you the intensity. Now, to put things in perspective, let us just get a feel for what you would expect in case you were doing geometrical optics. So, if you were doing geometrical optics, let us just consider a situation where you are doing geometrical optics. In geometrical optics, you would think of this. So, if you were to interpret this in terms of geometrical optics, you would think of this in terms of rays coming like this. You would think of this wave in terms of rays coming like this. All of the rays are in the same direction. I have made a mistake in drawing it, but all of the rays are in the same direction, and if you have rays in the same direction incident on the lens over here, and the direction is parallel to the axis of the lens, what the lens would do is it would focus all of these rays to a single point at the origin. So, if you were to interpret this situation where you have light falling on a slit, using geometrical optics, what you would expect to see on the screen is a bright spot at the center. And if all the waves, if all the rays in the incident wave had only a single wave vector, then all the rays incident would be in the same direction and they would be focused to the same point. So, in geometrical optics you would get a point, a very sharp point which has no size. So, it would be a very bright sharp point located at the center of the screen. You do not expect to get any size for it. So, in the geometrical optics interpretation of this experiment, if you were to interpret this whole thing and predict what you expect to see using geometrical optics, you would predict that you expect to see a very bright spot at the center of the screen and nothing else. Why a very bright spot? Let me again go through it. This wave would be interpreted in terms of rays. All the rays are parallel to the axis of the lens and they would all be focused to the same point at the center of the screen. But in reality this is not true. Light is a wave. So, in reality you do not get a single bright spot at the center. In reality what you get is a extended bright spot at the center, and there are other spots also located above this and below this bright spot. So, you have this fringe pattern. So, let us analyze this fringe pattern. So, this shows you the intensity as a function of theta. It is the same thing as this. I have now rotated this and plotted this along the x axis. Theta, varying theta means moving in this direction. That is what is shown over here. So, the intensity pattern is such that at theta equal to 0, which is at the center, I expect to get the maximum intensity. But then as I move away from the center, the intensity does not immediately fall to 0. There is a finite extent of the central bright spot. The intensity falls to 0. Let us ask the question, where does the intensity fall to 0? What is the width of the central bright spot? So, we have to look at the value of theta where the sinc, for which the sinc function is 0. And we know that so the function to look at is sin pi d theta by lambda divided by pi d theta by lambda, and we want to see where it assumes a value 0. So, this will assume a value 0 wherever pi d theta by lambda is equal to m pi plus minus m pi, where m could be 1, 2, 3 and any integer, or what it tells us is that it will be 0, the intensity will be 0 whenever theta is equal to m lambda by d. So, these are the zeros of the intensity. So, let us go back to the intensity pattern. So, the first, so that we at theta equal to 0, the intensity is maximum, and then as you increase theta, the intensity falls and it becomes 0 for the first time at an angle delta theta away from the center, and the corresponding value of theta wherever you have 0 is m lambda by d, and delta theta is just lambda by d. So, if you move an angle lambda by d from the center, you have the first 0. Same thing happens on the other side also. So, let us ask the question that we have this central bright spot. What is the width of the central bright spot? By width we mean the distance between the two zeros. What we mean is the distance between these two minimas. So, we see that this distance between here and here is 2 lambda by d. So, this is one of the big implications of the wave nature of light. If we had used geometrical optics to analyze this situation, as I have already told you, you expect to see only a bright spot at the center. But light is really a wave, and because of this you have the phenomena of diffraction. Instead of seeing a bright spot at the center, you get a finite size spot. The width of this bright spot at the center is not 0, but it has a finite width. The finite width is 2 lambda by d. So, the narrower the slit, the smaller the slit width, the larger is the width of the central bright spot. If you were to increase the width of the slit, the central bright spot would get smaller and smaller. Conversely, if you were to decrease the width of the slit, the central bright spot would get broader and broader. It would occupy a larger, the spread in the central bright spot would be more and more. This is what we see. The central bright spot has a width in angle which is 2 lambda by d. Now, beyond the first minima, you again have a maxima, and then you have the second minima. The second minima occurs at 2 lambda by d, then you have a third minima somewhere over here. The third minima occurs at 3 lambda by d. You have a maxima somewhere in between. The intensity of this second maxima, this is the first maxima, the intensity of the second maxima is considerably fainter than the first one. So, you have a sequence of bright spots. You will get one bright spot at the center, and then you will have a somewhat fainter bright spot here and here, and you will have a even fainter spot over here and here, because the intensity of this third maxima gets even smaller, and maybe beyond that you will have you might be able to see one more, and then it gets too faint. So, the intensity pattern looks like this. So, if this is the direction of the slit, you will get the fringe pattern in this direction, the same direction as the slit, and you will have the bright spot at the center. Then you will have a dark, the place where the intensity becomes 0, and again another bright spot which is much fainter than the central one, and another one, and so forth, and slowly it will get too faint to be observed. So, this is the intensity pattern produced by a single rectangular slit. We see that there are two main consequences of the wave nature which we encounter over here. The first thing is that the central bright spot is going to have a finite size. The size is 2 lambda by d, and the second consequence is that in addition to the central bright spot, we shall also have higher order maximas. We shall have a second order maxima, a third order maxima. So, beyond the central bright spot, you are going to have other bright spots because of the phenomena of diffraction. Let me now take up a small example to get a clear picture of the of what is happening. So, we will consider a situation where we have a slit whose diameter of size 1 millimeter. So, there is a slit, the slit looks like this. There is a plane wave incident on it, and the slit is of size 1 millimeter. The wave which is incident on it has a wavelength lambda. It is in the optical range. So, it has a wavelength 0.5, let us say 0.5 micrometers. So, what we have learned just now is that although the incident wave is a single plane wave, it has a unique wave vector. It is traveling in a unique direction like this. When the wave is sent through a slit, the wave that emerges is not going to be in a single direction, right? It is going to have a spread. How do we know that it is going to have a spread? It is quite clear from the intensity pattern over here. Just come back to this intensity pattern. What the lens does is that all the waves in a particular angle theta, it brings to a point. So, you see that the incident wave was only along theta equal to 0. So, you would have expected only a bright spot here, but what you see is that there is an intensity of light at other angle thetas also, which essentially means that when the wave has come out of the slit, there is some contribution, there is some wave propagating at other values of theta. So, for this value, for example, you would have some contribution in the wave So, the wave gets spread out, and we can say that approximately the spread in the wave that comes out, the wave that comes in has in one direction, the wave that comes out is spread over an angle which is this much. So, we can say that the wave is spread over this angle over from here to here, which is twice lambda by d. This gives us an estimate of the spread in the wave after it comes out through the slit. So, the question is that for a slit which is 1 millimeter in size, into which we have sent a plane wave with wavelength 0.5 micrometer, what is the spread in angle of the wave that comes out from the slit. So, this we have seen is 2 lambda by d, which in this case will be 2 into 5 into 10 to the power minus 7 meters divided by d, which is 1 millimeter, 1 into 10 to the power minus 3 meters. So, this gives us 10 to the power minus 3 radians. So, the wave that comes in is all going in a single direction. The wave that comes out is now spread over an angle 10 to the power minus 5 and minus 3 radians. So, this wave will be spread over an angle. The first maxima, the maxima at the center itself will be spread over 10 to the power minus 3 radians, and then there will be other maximas also which will be much smaller in intensity. There will be small amounts of wave coming out in other directions also, which will correspond to the second maxima, third maxima, but they have a much smaller intensity. The central bright spot itself will be spread over this angle. Now, the next part of the question is as follows. Suppose I put a screen which is 1 meter away. So, I have a screen and the screen is 1 meter away. The question is, what is going to be the size of the central spot that is going to be produced on the screen? So, that is quite easy to estimate. So, we will get a bright central spot over here, and the size of this central spot is going to be L, the distance which is L. In this case it is 1 meter. So, 1 meter into 10 to the power minus 3, that is the angle, the angular extent of the wave that comes out, and this. So, this is going to be 1 millimeter. Let us now ask the question, if I move the screen to a distance which is 10 meters instead of 1 meter, what is the size of the central bright spot? So, again we can do the same exercise, multiply this with the angle minus 3, and this is going to give us 1 centimeter. So, what we see is that this wave travelling in a unique direction, when you send it through a finite slit, when it emerges, it is spread out over a range of directions approximately of the order of 2 lambda by d. And if you put a screen far away, and or you put a lens and a screen, maybe not necessarily far away, then you will get a spot arising from this finite spread in the wave that comes out, and we have estimated the size of this spot for this particular slit. Let us now continue our discussion where we had left it. So, let us go back to the single slit problem. We had considered a situation where one dimension of the slit was much smaller than the other dimension L. So, D was assumed to be much smaller than L, and we had considered a situation where L is infinitely large, and the whole problem had reduced to a one dimensional problem in this direction. Now, let us ask the question, what happens when we also take into account this other extent of the slit L. Now, again we have to go back to the Huygen principle. Each point on the slit will contribute to the intensity at any point on the screen. So, if I want to calculate the intensity at any point on the screen, I have to add up the contribution from all of these points. But now you see it becomes a surface integral. I have to integrate over the surface of the slit. It is a two dimensional surface integral. Well, in this particular case the integral can be done, it is not very difficult. I will not go through the mathematics and I will just show you the result which I had shown you in the last class also. So, in this case you have a more general formula for the intensity pattern. It is now given by I naught sinc square beta x into sinc square beta y, where beta x and beta y are defined as beta x being pi d L, the length along the x axis is L. So, it will be pi L sin theta x, where theta x is the angle it makes to the x axis in the x direction. So, theta x, and there should be a factor of 1 by lambda. So, this whole thing divided by lambda is beta x and this whole thing divided by lambda is beta y. So, remember that d is the extent along the y direction, theta y is the angle it makes to the y axis in that along that direction and theta y is the angle it makes to the y axis, theta x is the angle it makes to the x axis, and we have a more generalized formula which holds in a situation where I have to take into account, where I have taken into account both the dimensions of the slit. So, let me show you the intensity pattern that you expect to see in such a situation. The intensity pattern that you expect to see in such a situation looks like this. Let me go through this in a little detail. So, first point to note is where is the intensity going to be brightest. It is quite obvious that the intensity is going to be brightest when theta x and theta y are both 0. Sinc function is 1 when theta x is 0 and this sinc function is 1 when theta y is 0. So, the intensity at the center is I naught. So, we have the brightest region at the center. Now, if I move only along the y axis, theta x remains 0. So, this sinc function remains 1. I do not have to bother about it. I only move along the y axis. Then I have the fringe pattern, a one dimensional fringe pattern essentially, because this factor becomes 0. It is just like a one dimensional fringe which we had just discussed, and the fringe spacing, the positions of the dark lines where it becomes dark is decided by this d. So, in this along the y axis, the fringes are going to be separated. This separation is going to be lambda of the order of, so the dark is going to be, this is going to be decided by lambda by d. So, the spot where the fringe becomes the darkest, this is going to be lambda by d. So, the spacing is going to be decided by the inverse of d. Similarly, if I were to move only along the x axis remaining at y, holding theta y 0, then it again would be another one dimensional fringe system. This factor would continue to be 1. So, I would have these fringes, the bright and dark spots along the x axis, and in this case the spacing would be 1 by L, and if I were to change both theta x and theta y, then both of these factors would come in. The intensity would fall off quite fast because the sinc function falls off with both this and this, and we have now have an understanding of this picture. So, as you move in this direction, the intensity falls off. As you move in this direction, so also does the intensity fall off, and when you move both along theta x and theta y, the intensity falls off even faster. So, you will see a few fringes which bright spots which will look like this, and then they will slowly fade away as you go further away. I have shown only the brightest parts of the fringe. Now, the point to note over here is what happens if you change d and L. So, when d and L are comparable, the fringe pattern will look like this. In this picture, this spacing is of the order of lambda by d, and this spacing is of the order of lambda by L. If I increase L keeping d fixed, so if I make the slit longer and longer in one dimension, then the whole fringe pattern is going to collapse, this spacing is going to get smaller and smaller, and for very large L you possibly will not be able to distinguish the fringes in this direction. They will all be very close together, and it will effectively, the fringe pattern is only going to be seen along the y axis, which justifies what we had what I had told you earlier. So, when you make L very large, if you make L very large, the entire fringe pattern is going to be very concentrated, this spacing is going to get very small. So, the entire fringe pattern is going to have a very small extent in this direction, and you will only see this extent of the fringes. Now, in yesterday's lecture and today's lecture, I have been discussing a rectangular slit, the diffraction pattern produced by a rectangular slit. Now, a rectangular slit is not so common. What we commonly encounter, the thing which is very important, let me now move on to that. What we commonly encounter is a circular aperture. So, this picture shows you a circular aperture. So, we have a screen over here. In that screen we have a circular aperture. So, there is a part of the screen which is a circle which has been cut out, and on this screen we have a plane wave which is incident. So, there is a plane wave which is incident. Now, if I put another screen very far away from the screen and see the image, or if I put a lens and a screen, if we had only the plane wave we would get just a spot, but we have seen that because of this circular aperture you will have the diffraction pattern, and for a rectangular slit we have worked out the diffraction pattern. You have to do the same thing over here. So, when you want to calculate the diffraction pattern due to a circular aperture, you have each point on this circular aperture will act like a secondary source, secondary wavelets will be emitted, and if you wish to calculate the intensity on a screen which is placed far away from this aperture, you have to add up the contribution from each of these sources. You now have a surface integral. The mathematics is a little more complicated, but so I will not go through it. I will just show you the resulting diffraction pattern that you expect to see on a screen located far away from this aperture, or if you put a screen and a lens if you put a screen and a lens like this, if you had a circular aperture here and you had this kind of a screen and lens arrangement, the intensity pattern that you would see on the screen over here would look like this. You would have a extended bright spot at the center, and then you would have a dark circular fringe around it, and then you would have the second maxima, which in this case is again circular because of the symmetry, circular symmetry of the aperture, and then again another dark line and again another circular fringe. The intensity of these higher order fringes, the first central spot is bright, the circular rings, the intensity slowly diminishes, and beyond a certain level you would not be able to see it. So, to explain this picture once more, if I had a circular aperture over here, if I had a circular aperture over here, it would produce an intensity pattern on the screen which would look like this. There would be a central bright spot, and then there would be a dark ring, and again a bright ring, a dark ring, a bright ring, and so forth, which is what I have shown over here. In the situation when we had a rectangular slit, we calculated the angular distance from the center to this. It was, so the angular distance between the center of the bright spot and where it becomes dark, the point where it becomes dark is, we had calculated this, it was lambda by d. We will not do the calculation for a circular fringe. I will just tell you the result. There is a small modification now when you do it for the circular aperture, and instead of being lambda by d, it is now 1.22 lambda by d. So, the central bright spot is now of radius 1.22 lambda by d, or of diameter 2.44 lambda by d, and then you have a bright dark ring around it, and then you have the second maxima and the third maxima and so forth, and then it gets fainter and fainter and you will not see it beyond a certain level. Let me now discuss, this is a very important, so what I have told you just now is something which is very important. Let me now discuss why this is so important. Let me just take up one particular situation, and the question that we are going to discuss is the resolving power of telescopes, the resolving power of telescopes. So, telescopes, as we know, usually have a circular aperture, right. So, here I have shown you the Hubble Space Telescope. You can see that there is a circular aperture over here through which light enters the telescope. Light which comes outside this circular aperture does not enter this telescope. This is true for all telescopes. So, for the Hubble Space Telescope, the circular aperture is of diameter 2.4 meters. So, the Hubble Space Telescope has a circular aperture. All telescopes, not only the Hubble Space Telescope, all telescopes have some kind of an aperture which lets light in. Usually this is circular. That is why we are discussing, that is the importance of the circular aperture. So, only light which comes in through this aperture is let in, light which comes outside does not get into the telescope, which is what I have shown over here. Similarly, this shows you the giant meter wave radio telescope GMRT, about which I have told you earlier. This works at radio wavelengths. The Hubble Space Telescope works at around optical and around the optical wavelength. This works at radio wavelengths. So, only the waves incident on this circular aperture gets collected. The waves that come beyond this are not collected, and the giant meter wave radio telescope has an aperture of diameter 45 meters. What is the implication of this? So, I have told you that all telescopes have some aperture and it is usually circular. The question is, what is the implication of this? The implication of this is as follows. Suppose I have a telescope, and let me just discuss it in words. Suppose I have a telescope and I point it towards a star. Now, a star is a source which is sufficiently far away, so that the light coming from the star can be thought of as a plane wave. So, the light coming from the star is a plane wave, it is all travelling in one direction, and if I think of it using geometrical optics, I pass it through a telescope. So, the telescope, I expect the telescope to focus all of this light to a single point. So, if I had two stars in my field of view and I point my telescope, in my image I expect to get 2 points. Unfortunately, this is not exactly so, and the reason why it is not exactly so is because the light which comes from the star is not cannot be thought of in terms of geometrical optics. It is actually a wave. So, when the light coming from the distant star passes through the circular aperture of the telescope, the image that is produced is not going to be a point, it is going to be the diffraction. It is going to be the diffraction pattern produced by the circular aperture. So, the image of a star produced by a telescope is actually going to be the diffraction pattern shown over here. You are going to have a central bright spot and then you are going to have bright rings around it. So, this is what you get. So, when you observe any star through a telescope, its image, the image that you are going to get from the star is not going to be a spot which you expect from geometrical optics. The image that you are going to get is the diffraction pattern of the circular aperture. Now, suppose I had two stars in the sky which are very close. So, one star is going to produce a central bright spot like this, and the other star is also going to produce its own central bright spot, and if the two bright spots overlap, the other fringes would also be there, but if the two bright spots overlap, then I cannot distinguish, I cannot say that there are actually two stars, because what I would see will be some big thing like this, and I would not be able to say that there are two stars. So, the question is, I would be able to say that there are two stars only if I had a situation where the two bright spots of the diffraction pattern of the two stars did not overlap. So, the question is, what is the criteria for me to be able to say that there are actually two sources and not one. So, I will stop this lecture here today. In the next lecture, I shall take up this criteria for discussion. It is a very important and interesting issue. So, I shall take it up afresh in the next lecture instead of introducing it right now.